Welcome to Lecture 57, continuing our exploration of the atomic nucleus, and in this lecture looking particularly at how we extract energy from the nucleus. And I remind you again that nuclear physics remains intertwined with history, with international policy. It also is intertwined with environmental issues, particularly global warming, because nuclear power affords a carbon-free way to energy. On the other hand, a way which is fraught with a number of perils. So let's begin by looking sort of theoretically at how we might extract energy from the nucleus, and then we'll look at how we, human beings here on Earth, do that in practice. So let me begin with a picture I showed in the previous lecture, a picture of a large atomic nucleus and the competing forces that both hold that nucleus together and tend to drive it apart. There's an electric force acting repulsively between all the protons in the nucleus, and now I want to think about the energy with which that nucleus is bound together. How tightly bound is that nucleus? A quantity called binding energy measures that tightness. And if we have protons repelling each other, that's tending to make the nucleus fly apart, and that is decreasing this binding energy, making it less tightly bound. The electric force is weak, but it extends again over long distances, as I pointed out last time. Then there's this attractive nuclear force acting between all the nucleons, neutrons and neutrons, protons and protons, protons and neutrons. It increases the binding energy because it's holding the nucleus together, but its range is it's strong, but its range is short. And the conclusion we drew last time from this is that more massive nuclei tended to have more neutrons than they did protons, whereas lighter nuclei tended to have equal numbers of them. Now we're going to draw a slightly different conclusion, related but different. And that is that the middleweight nuclei are the most tightly bound. They're the most tightly bound because if you start adding more protons beyond about the middleweight nuclei, you begin to lower that binding energy, lower the strength of the binding because you've got more of that repulsive force. Whereas if you start out with a very small nucleus and start adding nuclei, you get nucleons, you get more and more of that nuclear binding when they're close together. And that increases the binding energy. It's only when you start getting a big nucleus that the repulsive effect of the protons lowers the binding energy. And in consequence, there is a very famous graph called the curve of binding energy. By the way, it was a subject of a book by the writer John McPhee. And the curve of binding energy plots nuclei by weight along the bottom, starting with hydrogen, the lightest, to uranium, the heaviest naturally occurring nucleus. On the vertical axis is the binding energy, not the total amount of it, but the binding energy per nucleon. So you take all the nuclei, all the nucleons in a nucleus, and you take the binding energy and you divide by the number of nucleons, and you get a measure of how tightly bound the individual nucleons are. And that curve looks something like this for the reason I just said. You start out with hydrogen, there's no other nucleons, so there's no binding energy. You build up to successively more massive nuclei, and at first you increase the binding energy because of that strong nuclear force. But when you get big enough, and it turns out to be right at about where iron is located in this continuum of nuclei, then the repulsive effects of the protons begins to lower the binding energy. And what this all means is the following. It means that there are two ways that you can combine or alter nuclei in order to release energy. One is to fuse very light nuclei, because if you take light nuclei, which are not very tightly bound because there isn't much nuclear force because there aren't many nucleons, and you bind them together into a somewhat heavier nucleus, then energy will be released as that heavier nucleus is more tightly bound. One example, important example, is the fusion of hydrogen to make helium. That's what powers the sun. More on that toward the end of the lecture. So that's one way you can achieve energy release from nuclear interactions, by fusing light nuclei together. You can also break heavy nuclei apart. That's the process of nuclear fission. Nuclear fission takes heavy nuclei because they aren't quite as tightly bound as middleweight nuclei. You break them apart into two middleweight nuclei, and there's tighter binding with the two middleweight nuclei, and so in the process you have released some energy. So fission and fusion are two different, distinct processes whereby we can release energy from the atomic nucleus, and they come about because of the shape of this curve of binding energy, and they both tend to move us toward middleweight nuclei in the vicinity of iron, but plenty of other middleweight nuclei. Now, in principle, you can do these energy-releasing reactions with any nuclei. In practice, it's difficult. In particular, fission is very difficult to make happen under most circumstances with just any random heavy nucleus, although in principle, it can be done. So that's the curve of binding energy, one of the crucial ideas in understanding how we release energy from the nucleus. Let's take a look at nuclear fission. But before we do, I have to take a little diversion into history, because the history of nuclear fission is fascinating, and like other nuclear issues, it's tightly intertwined with the history and the fate of human civilization. Nuclear fission was discovered in the 1930s, in the very late 1930s. Throughout the 1930s, a number of physics labs around the world were doing experiments in which they were bombarding nuclei with neutrons, which is a useful thing to do because neutrons, being uncharged, aren't repelled by the positive nucleus, and so they can go right into it and they can cause nuclear reactions, and you can study nuclei. So a number of labs around the world were performing these experiments. And in particular, a lab in Germany with chemists Hahn and Strassmann were doing this experiment, and they were bombarding nuclei, and in particular, they chose to bombard uranium, and they bombarded uranium with neutrons, and they discovered something very strange in their results. They discovered that their final product after doing this bombardment was contaminated with sort of middleweight nuclei, particularly barium, which has atomic number 56. Where on earth did the barium come from? They were chemists. They were collaborating with a physicist, Lisa Meitner, and she had to leave Germany. In 1938, things were uncomfortable for her. She fled to Sweden, and she was in Sweden at the time that these results were becoming known. So she's on the other side of the divide that was building just before World War II. And in late 1938, she and her nephew, Otto Frisch, were on a walk in the Swedish countryside, and she suddenly realized what had happened. She drew a picture showing uranium breaking into two equal-sized pieces. Before that, all the nuclear reactions people had studied involved small chunks like alpha particles coming out of a radioactive material. Suddenly, uranium seemed to have split in two. And she and Frisch published a paper. They coined the term fission for the first time, and the paper was published in January of 1939 in Nature magazine. And this is on the eve of World War II, and the implications were obvious, because in that paper they calculated the energy that would be released. They calculated in two ways, one by looking at the electrostatic repulsion of these two nuclei that would be created, and one by looking at the Einstein E equals mc squared mass difference, and both ways they came up with a colossally large number for the energy that would be released in this process, and immediately it was understood that this had serious military implications. Rarely has a fundamental discovery gone so quickly to practical realization. A few short months later, we had a team of physicists going to meet Albert Einstein and telling Einstein about this and saying, Einstein, write a letter to President Roosevelt telling him about this new discovery and about how we have to get a program going to try to build a weapon based on nuclear fission. Einstein had nothing else to do with nuclear fission, by the way, but he used his great name, signed that letter, and that initiated the Manhattan Project. By 1942, a team led by Enrico Fermi in Chicago, at the University of Chicago, had built the first successful nuclear reactor and got it going, a critical chain reaction, in 1942. And of course, in 1945, one nuclear weapons test followed by two nuclear weapons used against Japanese cities. So that's the history of nuclear fission. It's a very short, abbreviated history, and there it is. Let's look now at the physics of nuclear fission. So there are two ways to make nuclear fission happen. Sometimes it happens spontaneously. Rarely, a massive nucleus will simply spontaneously split in half. Very rare. Much more important for our purposes is neutron-induced fission. That's the process that Hahn and Strassmann were studying, where a fissionable isotope is bombarded with neutrons. Fissionable isotopes are isotopes that will undergo fission when they're struck with neutrons, sometimes with very high energy, and they include uranium-235, uranium-238, and most other heavy nuclei if you hit them with high enough energy neutrons. There's a very common misconception here. The word fissionable is commonly misused to mean only uranium-235 and a couple of other isotopes which have a more important special property. Those isotopes are called fissile, and they will undergo fission if they're struck by low energy neutrons. And they include uranium-233, uranium-235, and plutonium-239. And I want to maintain that distinction. It's a really important distinction, and it's a common misunderstanding. So when I say fissionable isotope, I mean an isotope that can be made to fission if you strike it with a neutron. Maybe it has to be a very high-energy neutron. When I say a fissile isotope, I mean one that will undergo fission even if you strike it with quite a low-energy neutron. In fact, in some cases, it's more likely to undergo fission with a low-energy neutron. So that's the idea of nuclear fission. How does neutron-induced fission work? Well, here's a uranium-235 nucleus. In comes a neutron, gets absorbed, delivers some energy to the nucleus. The nucleus becomes uranium-236 because it's still uranium, but it has picked up an extra neutron, and it undergoes an oscillation. It gets unstable. So here is the nucleus. I've colored it pink to remind you that it's positively charged, and I've shown the two positive charges there to show you that the opposite ends of it are, in particular, positive charge. And it tends to oscillate back and forth. And eventually, that positive charge that's getting pushed, that's getting farther and farther apart, is tending to pull that nucleus apart, and eventually it forms this dumbbell shape, and then it breaks apart into two roughly but not exactly equal-sized pieces, two middleweight nuclei. And typically, in neutron-induced fission, out come 2 or 3 neutrons. Average is about 2 point something. Sometimes more, sometimes less. There is no one reaction for nuclear fission. There are many reactions, but basically, neutron comes in, uranium splits into 2 roughly equal mass middleweight nuclei, but slightly different masses, and out come some neutrons. That's the process of neutron-induced fission. Here's what neutron-induced fission looks like if we write it down as a reaction. In this particular case, in comes a neutron, charge 0, atomic number 0, mass number 1, hits uranium-235, 92U-235, forms X and Y, where X and Y are those two so-called fission products, those middleweight nuclei, and it also forms B, where B is a number typically between 2 and 3 of additional neutrons. And that's going to be really crucial to understand how fission occurs and how we maintain a fission chain reaction, which we'll get to shortly. So that's a formula for neutron-induced fission. Something else comes out of fission, as well as neutrons and these fission product nuclei. That is fission energy. About 200 million electron volts per fission. Now, you probably don't have a good feel for an electron volt, but let me give you a good feel for what that means. First of all, here's how that energy is divided. Most of it comes out as the kinetic energy of those fission products. But a little bit of it comes out as the energy of neutrons, some of it comes out as gamma rays, very high energy photons, and some of it comes out as beta radiation, which is actually the result of extremely short-lived fission products decaying rather quickly. Compare that with about 4 electron volts you get for the reaction carbon plus oxygen gives CO2. That's the reaction of burning coal. 200 million electron volts from a nuclear fission event, 4 electron volts from this particular chemical reaction. I call that the nuclear difference. It's a factor of somewhere on the order of 10 to the 7, 10 million, between nuclear and chemical reactions. We can quibble about whether it's 1 million or 10 million or 100 million. It doesn't really matter. It's the nuclear difference. It's a colossal difference. That's why nuclear fuels are such concentrated sources of energy. That's why you can carry a bomb in a suitcase and blow up an entire city with it. That's why, although we are generating a lot of nuclear waste we don't know what to do with, we're generating a lot less nuclear waste in volume than we are waste from coal-burning power plants, for example. The nuclear difference explains all those distinctions. The nuclear difference is a factor of about 10 million between nuclear reactions and chemical reactions. And I would argue that there is some level at which a difference that big ceases to be merely quantitative. It becomes a qualitative difference between nuclear things and chemical things. Nuclear energy is a totally different kind of energy. It is just that much more concentrated by a factor of about 10 million. Let me give you one example. Here's a picture that illustrates the nuclear difference. At the top, we see a power plant way in the distance. It's a coal-burning power plant out in the American Midwest. And this particular power plant is fueled each week by 14 trainloads of coal, each carrying 110 cars. And those cars come in, the train comes in, the train stops on a track, a big machine picks up each car, dumps the coal, the train shuttles on, next car dumps the coal, train shuttles back to an open pit mine in Wyoming, next train comes in. This goes on almost round the clock, 2 train loads a day, 14 train loads a week, 110 cars each train. The picture down at the right is the refueling operation for a typical nuclear power plant. It gets a couple truckloads of nuclear fuel being unloaded here, as you see, and that happens about every 18 months. So that's the nuclear difference. What a colossal difference, and it's due to that huge difference in the energies that are released in nuclear versus chemical reactions. Let's do a quick thing on our big screen to see if we get this process of nuclear fission. So let's look at nuclear fission, and I'm going to tell you a particular fission reaction produces the isotope krypton-92. By the way, that's an inert gas. It's a very common nuclear fission product, but it isn't a particularly dangerous one because it's an inert gas. It doesn't react chemically, and it goes off into the air and gets dispersed. And this particular reaction produces also 3 neutrons. And so what is the other fission product? That's our question. So here's the fission reaction. Fission reaction consists of a neutron coming in, hitting uranium-235. I'm going to skip the intermediate uranium-236, and we get out of this krypton-92. Krypton's atomic number is 36. This one's mass number is 92. And we get some other daughter nucleus or some other fission product, which I will call Y. I don't know what it is, and I don't know what its atomic number is, and I don't know what its mass number is, and I'm telling you 3 neutrons also come out. And a neutron, again, has no charge, so no atomic number, but 1 mass unit. So there's our fission reaction, and we have to figure out what A and Z are, and that will let us identify what this product is. So let's do the numbers. Well, on the left, we have 1 mass unit and 235 mass units. On the right, we have 92 mass units in the krypton, 3 in the 3 neutrons. And we don't know how many in this other product Y, but we can solve now, and we get A equals 141. So now we know the atomic number of the mass number of the product is 141. Let's do the same thing for the atomic number, equivalently electric charge. The neutron is uncharged. The original uranium nucleus has 92 protons. On the right, we've got 36 protons in the krypton. The neutrons have no charge, so that's 0. And we have Z, the unknown atomic number of the product. Solve for that. Z is 56. So we're almost there. We've got the numbers. That characterizes our isotope. Take a look at the periodic table. Element with atomic number 56 is barium. In this case, we have a mass number 141, so the product is barium-141. That, by the way, is the barium that showed up in Hahn and Strassman's experiments when they bombarded uranium with neutrons, and that is the product that Lisa Meitner then explained in her description of the process of nuclear fission. So that's how nuclear fission works, and there we've identified one particular fission product, which is commonly found in the byproducts of nuclear fission. Well, let's move on. Fission products, it turns out, are quite radioactive, and I want to show you why in a very fundamental way they're radioactive. So here's a diagram I showed you in the previous lecture. It's the chart of the nuclides. It plots neutron number along the bottom, proton number along the vertical axis. For a while, proton and neutron numbers are equal, but then this curve bends over for the reasons I described before, namely you need more neutrons to glue those heavier nuclei together against the repulsive force of their distant protons. Now let me take that curve and just draw a simple graph through the middle of it to show you its general shape, that downward arcing shape as it goes onward toward more heavy nuclei. Again, at the top left, we have nuclei with too many protons. They're unstable because of the repulsive electric force. At the bottom, we have too many neutrons. They're unstable because the neutron decays. Basically, beta decay occurs. Up here is uranium, the heaviest naturally occurring isotope. If I split uranium into 2 pieces, those pieces are going to have approximately the same ratio of neutrons to protons as did the original uranium. It won't be quite exactly the same because A, they might not distribute exactly the same, and B, a few neutrons come out right away. But it's going to be close to the same ratio of neutrons to protons that uranium has. And that means the fission products are going to lie somewhere along that straight dashed line from uranium going down to 0. So they're somewhere in there, and I've actually shown you these 2 blobs because what happens is the fission products never come out exactly equal, and they tend to distribute themselves into 2 ranges on either side of exactly half the uranium nucleus's size. So there are the fission products. But the crucial point about this diagram is it is fundamental to the nature of fission products that they lie below that curve of stable isotopes, and they have too many neutrons, and so they undergo beta decay. They are intensely radioactive. The fission products are intensely radioactive. That's why after the accident at Fukushima in Japan, the reactors shut down. They were stopping producing nuclear energy by a chain reaction, but they were continuing to produce nuclear energy, which manifested itself as heat, by the decay of these highly, highly radioactive fission products. That's not a problem with the design of the reactors or anything else. It's the nature of nuclear fission. When you make nuclear fission happen, you make highly, highly radioactive fission products. Far more radioactive, by the way, than the original uranium, with its 4.5 billion year half-life being hardly radioactive at all. But these fission products have half-lives from seconds to typically tens of years or so, maybe centuries in one or two cases. They're pretty short, and so they must be intensely radioactive to decay that quickly. So that is the origin of the radioactive fission products. There are other radioactive materials produced in the fission process. For example, when U-238 absorbs a neutron, U-238, not the isotope that fissions, but U-238, it leads to plutonium and other so-called transuranics, which are heavier than uranium nuclei that have half-lives short enough that they don't tend to occur in nature. They tend to have longer half-lives in the thousands to tens of thousands of years and longer, and so they're a little more thorny to deal with, but they're less radioactive because they have longer half-lives. They decay more slowly. And one particular reaction is important, and that's the reaction neutron hitting U-238 makes U-239. U-239 undergoes a beta decay. There's the electron coming out and becomes Neptunium-239, element 93. That decay at 24-minute half-life. The neptunium decays by another beta decay to element 94, which is plutonium. This is plutonium-239. There's a half-life of that decay of 2.4 days, and then we're stuck with the plutonium because it has a half-life of about 25,000 years. It can get hit by more neutrons and make other heavier isotopes of plutonium and other things, but if we get plutonium-239, we have a relatively long-lived isotope. And like uranium-235, plutonium-239 is fissile. It can be, quote, burned in a reactor. In fact, one of the reactors at Fukushima, the one that was causing the most worry, was actually fueled by mixed uranium and plutonium fuel. And because plutonium's 25,000-year half-life is much less than uranium's 4.5 billion year half-life, plutonium is a lot more dangerously radioactive, so there was a lot of worry about that. The other worry about plutonium is it can be used to make bombs, and you can extract it from a reactor and use it to make bombs. So that's a bit of a problem. Now, how do we actually technically extract energy from nuclear reactions? Well, what we do is create what's called a chain reaction. So I'm showing you here a bunch of fissile nuclei, uranium-235 or plutonium-239. In comes a neutron. It strikes one of these fissile nuclei, causes it to fission, and out comes some more neutrons. And neutrons are what cause fission. So those neutrons cause more fission, and more neutrons come out, and more neutrons, and so on. And pretty soon the whole mass of fissile stuff has undergone fission. In fact, if you just have a solid mass of plutonium or uranium, it will fission in about a microsecond and release the energy equivalent to thousands and thousands of tons of coal. That's a nuclear fission bomb. I'm not going to say any more about bombs here, but I'm going to point out that making a fission reaction go out of control is not a terribly difficult thing to do, unfortunately. Now, what's the likelihood of fission happening? Well, that depends on which isotope you're working with. Uranium-235 is extremely likely to fission if it's hit by a slow neutron. It will fission if it's hit by one of those fast neutrons coming out of a fission event, but it's less likely, and it will fission for even faster neutrons. Uranium-238, it's nearly impossible to make it fission with slow neutrons. That's why it's not fissile. It's even very unlikely for uranium-238 to fission with fast neutrons coming out of the fission process, but very fast neutrons, and by the way, this happens in a so-called hydrogen bomb, which actually gets about half of its explosive yield from uranium-238 because of very intense neutron fluxes being generated by fusion. It's probable that with very fast neutrons you can fission U-238, but in our nuclear reactors, U-238 does not get fissioned, although some of it turns into plutonium-239, which does. How do we sustain this chain reaction? Well, we have to ask the question, if I have a fission occur, it gives out 2 or 3 neutrons, how many of those cause additional fission? That's called the multiplication factor. If it's less than 1, the reaction is subcritical and it fizzles out. If it's more than 1, the reaction grows exponentially and you've got that explosion. If it's exactly equal to 1, you get a steady power output. And that's what we want in a nuclear power reactor. Well, what happens to these neutrons? Why don't they all cause fission? Well, they might. They might strike a U-235 and cause fission. Much more likely if they're slow neutrons. They might escape the fuel altogether. They might strike something else and get absorbed, like a proton in water and make deuterium, U-238, and make plutonium. They might strike fission products and be absorbed. They might strike substances that you put there intentionally to absorb neutrons. You may have heard after the Fukushima accident they were adding boron to the water they were pumping into the reactors because boron is a strong neutron absorber and that absorbs the neutrons and inhibits the possibility of a chain reaction occurring. But out of all this comes the possibility that there is a critical mass, a certain amount of fissile material you need to get together in one place. And exactly what the critical mass is depends on the shape and the purity and what you're doing, whether it's a reactor or a bomb. But we know that the critical masses are on the order of pounds for pure uranium and plutonium, which is a very scary fact because it means you can make bombs out of relatively small amounts of these materials. What are the implications of this critical mass and these other properties for nuclear technologies? Well, one thing is we have to enrich uranium to make reactor fuel. Natural uranium is 99.3% uranium-238, only 0.7% uranium-235. So it's a tiny, tiny fraction of U-235. If you want to make reactor fuel, you've got to bring it up to 3 to 4%. If you want to make bomb fuel, you've got to bring it up to about 80%. If you have the technology to make reactor fuel, you automatically have the technology to make weapons also. That's one of the reasons for great worry about the proliferation of enrichment technology, which is something the world is very much concerned about these days. If you have nuclear power, you would also like to slow those neutrons down because the slow neutrons are more likely to cause fission, and so you need something called a moderator in a power reactor, and it's typically water. And with nuclear power, you also want to control, so you have some kind of neutron absorber control rods that you can move in and out of the reactor. And the end is most of our nuclear fission reactors in the world look something like this. They have uranium in fuel rods. They have control rods that can be moved in and out to absorb neutrons and control the rate of reaction. Cold water comes in, and either hot water or steam, depending on the design, comes out and makes a turbine spin and makes electricity. That's a nuclear fission reactor. Many designs throughout the world, but the most common ones use ordinary water as both the moderator and the coolant that carries the heat away from the fission reaction. Let me just take a few minutes and end by talking about the other way of making nuclear energy, and that's fusion. That fusion joins light nuclei to make heavier ones, releasing energy in the process. It's what powers the stars. It's responsible for making most of the elements beyond hydrogen and helium, as we'll see subsequently. It is used in thermonuclear weapons, but we haven't yet harnessed it for energy generation here on Earth. Here's how the sun does it. The sun fuses protons and makes a sequence of reactions, which I'm showing here, occur. Those reactions occur, and ultimately the net result is you've taken 4 protons, 4 hydrogen nuclei, added them with 2 electrons, and made a helium-4 nucleus and a lot of energy, about 27 million electron volts. So that's how the sun does it. And there's a kind of picture of that reaction. We are, in fact, made of stardust because fusion in stars more massive than the sun continues. The sun's going to stop with helium, but more massive stars with greater pressure and higher temperatures continue that process, and they forge ever heavier elements up to iron. And so very massive stars have this ring-like structure with elements like carbon and silicon and oxygen in different rings. And when those stars go supernova, if they do, they spew those elements out into the interstellar medium. And by the way, during those supernova events, some of the even heavier elements, like, for example, uranium, get created. And the supernova explosions spew that material into interstellar space. They also create these heavier elements, and that forms new stars and planets and us. So we are literally made of stardust. We're made of materials, the carbon that's essential to life, the oxygen, the silicon, all the elements that make up our everyday world. Silicon is the second most abundant element in Earth's crust. These things were all forged in these fusion furnaces in the interiors of long-dead, massive stars that went supernova. We're stardust. We're still trying to make fusion happen on Earth. The easiest way to make it happen is not with protons, but with deuterium and tritium, the 2 heavier isotopes of hydrogen, and we can join them to make helium, and a neutron comes out and a lot of energy. And we're trying 2 ways of doing this. Magnetic confinement would confine a plasma, a hot ionized gas, at 100 million kelvins temperature. No material substance can maintain that in a so-called magnetic bottle. We're building this item shown here. It's called ITER. It's being built in France, and it may operate in about 2022. And if it operates successfully, it will produce more fusion energy than it was put in to make the fusion reactions happen. But it won't be a fusion reactor or power plant yet. At Lawrence Livermore Laboratory in California, we have this inertial confinement device, a fusion device called the National Ignition Facility, and it blasts tiny deuterium pellets with 192 laser beams and tries to produce fusion. That way, it's actually a little bit ahead of the game. It's actually fired its lasers early in 2009 and 2010. It got going. It has not produced break-even fusion yet, but it may get there before the magnetic confinement device. It's also, by the way, a way of studying nuclear bomb explosions, because these are miniature explosions. If we succeed in getting nuclear fusion to work, then 1 gallon of seawater, based on the 1 in 6,500 hydrogen atoms in it, this deuterium, will be the equivalent of 350 gallons of gasoline in its energy. And we will have unlimited energy that will last for 25 billion years, 5 times as long as the sun is going to continue to shine. So some physicists think this is a boondoggle, we'll never make it work. But it certainly is an almost inexhaustible energy source if we could get it to work, so I think we ought to be pursuing it. Well, let me wrap this all up with the summary of this lecture. We saw the curve of binding energy, that important curve that establishes 2 ways of getting energy out of the atomic nucleus, fission and fusion. Nuclear fission we looked at in some detail, its chain reaction in U-235 and plutonium-239. We looked at some constraints that the physics places on our nuclear technologies, and then we took a look at fusion in stars, possibly for terrestrial energy production, and the ultimate goal of getting really almost inexhaustible energy from seawater.